We live in a world awash in digital images. Billions of smartphones and cameras capture countless moments every day. These images document our lives, fuel our creativity, and drive scientific discovery. But there's a catch. Digital images are susceptible to noise. Noise is the enemy of a clear picture. It manifests as graininess, speckles, or other unwanted artifacts. Noise can obscure details, reduce image quality, and even fool image analysis algorithms. Several factors contribute to noise in images. Low light conditions often lead to increased noise. Sensor limitations and digital processing can also introduce unwanted artifacts. The impact of noise is significant. In photography, noise can ruin a precious shot. In medical imaging, it can obscure crucial diagnostic information. In astronomy, it can mask faint celestial objects. Clearly, we need ways to combat image noise. Before the deep learning revolution, we tackled image noise with traditional denoising algorithms. These methods relied on mathematical models and assumptions about the nature of noise and the underlying image. One common approach was linear filtering. Linear filters, like the Gaussian filter, average pixel values within a neighborhood. This averaging smooths out noise but can also blur sharp edges. Another technique was median filtering. Median filters replace a pixel's value with the median value of its neighbors. This is effective at removing salt and pepper noise but can distort fine textures. These traditional methods had limitations. They worked well for simple noise patterns but struggled with complex noise. They often required manual parameter tuning, making them less practical for large datasets. And they struggled to preserve fine details while removing noise. A new approach was needed. Enter deep learning, a branch of artificial intelligence that has taken the world by storm. Deep learning algorithms, inspired by the structure of the human brain, excel at learning complex patterns from vast amounts of data. This ability proved transformative for image denoising. Deep learning models, in contrast to traditional methods, don't rely on handcrafted rules. Instead, they learn the characteristics of noise and clean images from training data. This data-driven approach allows them to adapt to different types of noise and image content. The results have been astounding. Deep learning has ushered in a new era of image denoising. It has enabled us to achieve unprecedented levels of noise reduction while preserving image details. This has had a profound impact on various fields, from consumer photography to scientific research. At the heart of many deep learning image denoising models lie convolutional neural networks, or CNNs. CNNs are specifically designed to process data with a grid-like structure, like images. They employ convolutional filters that slide across the image, extracting features and patterns. These filters learn to recognize different aspects of the image, from edges and textures to objects and scenes. By analyzing the image at multiple scales, CNNs can capture both local details and global context. This makes them highly effective at distinguishing noise from the underlying image content. CNNs have become the workhorse of image denoising. Their ability to learn complex image features and their computational efficiency make them well suited for this task. Many variations of CNN architectures have been developed, each with its strengths and weaknesses. Section 5. Generative Adversarial Networks, a dance of generator and discriminator. Another powerful deep learning approach for image denoising is the Generative Adversarial Network, or GAN. GANs consist of two neural networks locked in a game-like competition, a generator and a discriminator. The generator's goal is to create realistic images that mimic the training data. The discriminator's job is to distinguish between real images from the training set and fake images generated by the generator. Through this adversarial process, both networks improve their abilities. GANs have shown remarkable ability to generate high-quality images, making them well-suited for denoising. They can learn to generate clean images that preserve fine details while removing noise. However, training GANs can be challenging, requiring carefully chosen architectures and training procedures. Section 6. Training the machines, supervised versus unsupervised learning. Deep learning models need to be trained on large datasets to learn effectively. There are two main approaches to training denoising models: supervised and unsupervised learning. Supervised learning requires pairs of noisy and clean images. The model learns to map noisy inputs to their corresponding clean targets. This approach typically yields good results but requires a large dataset of paired images, which can be difficult and expensive to acquire. Unsupervised learning, on the other hand, doesn't require clean target images. The model learns to remove noise by exploiting the statistical properties of noise and clean images. This is more challenging but has the advantage of not requiring paired training data. Both approaches have their merits and are actively researched. Section 7. Datasets and benchmarks, the testing grounds for denoising AI. The development and evaluation of image denoising algorithms rely heavily on standardized datasets and benchmarks. These datasets provide common ground for researchers to compare their methods and track progress in the field. One widely used dataset is the BSD68 dataset. BSD68 contains 68 natural images with different noise levels added, making it suitable for evaluating denoising performance on a variety of image content. Another popular dataset is the Kodak PhotoCD dataset, which consists of 24 high-quality images commonly used to benchmark image processing algorithms. These datasets, along with standardized evaluation metrics, allow researchers to objectively assess the performance of their denoising models and compare them to the state-of-the-art. This fosters innovation and drives progress in the field. Section 8. Evaluating success. How do we measure denoising prowess? Evaluating the performance of image denoising algorithms involves quantifying how well they remove noise while preserving image details. Several metrics are commonly used for this purpose. Peak signal-to-noise ratio, or PSNR, is a widely used metric that measures the ratio of the maximum possible signal power to the power of the noise. A higher PSNR generally indicates better denoising performance. However, PSNR doesn't always correlate well with perceived image quality. Structural Similarity Index, or SSIM, is another metric that compares the structural information in the denoised image to the original clean image. SSIM values range from 0 to 1, with 1 indicating perfect structural similarity. These metrics, along with visual inspection of the denoised images, help researchers assess the effectiveness of their algorithms and guide further improvements. Section 9. The future is bright. Challenges and opportunities in AI denoising. Deep learning has revolutionized image denoising, but challenges and opportunities remain. One challenge is developing denoising models that generalize well to different types of noise and image content. Real-world images can contain a wide variety of noise sources and artifacts that may not be well represented in training datasets. Another challenge is balancing noise reduction with detail preservation. Removing too much noise can result in an overly smooth image that lacks fine details. Finding the right balance is crucial for achieving visually pleasing and informative results. Despite these challenges, the future of AI denoising is bright. Researchers are exploring new deep learning architectures and training methods to further improve denoising performance. They are also developing denoising models for specific applications, such as medical imaging, astronomy, and microscopy. As AI continues to advance, we can expect even more impressive image denoising capabilities in the years to come.